So for this project, we have PJ Sun from IBM. He will chair this project together with Real Espandia and Hammond Shah from Intel. I'm Haley from iNEMI. I will help with the project management. Okay, PJ, can you go to the next slide? Okay, so for today's agenda, I will firstly introduce the chairs, then talk about the iNEMI project development process, how we get to here, and the document that defines this project and what we are going to accomplish. Then PJ and Real will introduce the background, objective, the details of this project. Then I will explain how to participate. At the end, we will open for Q&A. Next. So PJ is from IBM. He's the senior technical staff member with over 42 years experience in the metallurgical engineering and FA of computer power packing and cooling. In recent years, he has been working on the superconductor manufacturing and catalyzation on the thin film technology and also the electromigration catalyzation. He holds 86 patents. Our next chair is Real Espandia. He's the senior packaging engineer at Intel. He has been with Intel for over 37 years on developing board assembly materials and processes. He published over 70 papers, mainly in the SMT fields. He's also the very active member at SMTA. So Real has been the chair for the iNEMI project on low-temp solder process and reliability. Hammond Shah, he's the senior R&D engineer at Intel with 11 years experience on the next generation board assembly and materials development. He's a co-lead within Intel for the low-temp solder technology. He is also experienced on the materials quality and reliability. Okay, next. For iNEMI, when we have a project, I think similarly as what you do within your company, we will go through some steps. We have a process we call a stage gate process in place to make sure the project is well defined and has high possibility to make it a success. Okay. So we have been in through the concept definition and planning to clarify the project scope, what we are going to accomplish. It will be defined in the planning phase, the statement of work, and also we have a project statement agreement generated to define the resource commitment and the project management roles. So now we are in the launch phase. It's to open, to communicate within the industry, because some companies who may interested in this project may not see involved in the earlier definition of planning stage. So this gives a chance to have people review the opportunity to participate in this project. So the launch will open until the end of this month. This project will officially start in February to execute the tasks planned. Okay, that's the steps we will go through. Then we will have the closure report when we finish the objective. Right? Then this project during the planning phase, it's open for the industry inputs. So even non-members can be involved in the planning, but when we get to the project execution, it's limited to the committed members because there is a shared information and resource. The project management rules need to be followed. Okay, thank you. Next slide. PJ, next. Okay, so we have two documents for any iNEMI projects to describe first the SOW sets out the project scope, background, purpose, required resource, the project schedule, the tasks need to be accomplished. The project statement, that's the document will need to be signed by the participating companies to secure the commitment on resource, time contribution, and comply with IP policy, the project management rules. Okay. So as already mentioned, the membership will be required to participate in this project. So for existing iNEMI members, if you decide to join this project, just sign this project statement. If you are still not a member of iNEMI, but want to join this project, you can discuss with iNEMI staff. You can communicate with me as well about the membership. So there is a membership agreement need to be signed. It's to agree with the iNEMI bylaws and our policies. Right. Next. Okay, I think I will pass over to PJ to introduce the background of this project.
Okay, great. So this is PJ Singh. First, let me spend a couple of minutes on defining what is electromigration and how does it differ from ion migration, which is also electrochemical migration. So electromigration is the biased diffusion of atoms in a metal due to momentum transfer from flowing electrons. So when electrons flow in a metal, they have momentum and they can bang the atoms in the metal, and these atoms can diffuse preferentially in the same direction as the electron flow. So basically, in electromigration, the metallic atoms move in the same direction as electron flow. So everything's solid state. There is no electrolyte. In the case of ion migration, which is also electrochemical migration, this happens in between two metals which are connected, which are bridged by an electrolyte. So let's suppose you have two copper metallizations on a circuit board, and you have contamination in between, and this contamination is ionic. So because of potential, the metal ions can dissolve into the electrolyte, and there's moisture there. So you could get what's called dendritic growth. So you can see this tree-like structure forming. So these dendrites can short circuit the metallization on a circuit board. So that's ion migration. So electromigration happens in metal, whereas ion migration happens in an electrolyte. So that's the big difference. So some background information. We find that we have tin bismuth as a very attractive low melting alloy, and iNEMI has done a lot of mechanical studies showing the advantages of using tin bismuth alloys for low temperature solders. So one reason we like to use low temperature solders is because of warpage of high-density microelectronic packaging that is becoming so commonplace. Also, if you're doing hierarchical soldering, which means you have many soldering steps, so the later soldering steps should not melt the earlier solder joints. So that's where the tin bismuth would come in handy. This would be probably the last solder joint you make with the tin bismuth solder. The problem with tin bismuth is that it has very high propensity for electromigration. If you see this sketch on the right side, on the top, you have copper metallization. On the bottom, you have copper metallization, and it's soldered by tin bismuth in the middle. If electrons are flowing up through this solder joint, then because of electromigration, the bismuth will move upwards and it'll segregate at the top interface between the copper and the tin bismuth. And bismuth, this bismuth segregated at the top will be almost pure bismuth. It's very brittle. So you could get, you have two major problems because of this. One is the electrical resistance of the joint will increase. The second is the brittle nature of the bismuth may cause cracking in the joint. So what we want to do is to explore ways to mitigate these shortcomings and to develop a tin bismuth solder that can maintain performance and reliability over the product life. So just as an example on the bottom right, this is a LGA between a component and a circuit board. And you can see bismuth layer, which is formed on the bottom copper surface. So the bismuth is segregated. And so this is the problem that we are addressing in this project. So some more background on electromigration. There's a phenomena called back stress. So if you look at this orange box in the middle of the page, consider that as tin bismuth solder, and electrons are flowing towards the right, shown by this black arrow. So that'll push the bismuth towards the right. So there'll be a stress gradient. There will be very high compressive stress on the right and tensile stress on the left. So that stress gradient will push the atoms back to where they came from. So that's the back stress. So in 1976, Elon Black discovered this phenomena. And he also said that if you have a given current density, let's say J, J is known, the current density is known. So there will be a joint height below which electromigration will not occur because of back stress. Or for a given joint height, there will be a current density below which electromigration will not occur because of back stress. If you look at this plot, the vertical axis is ion velocity. This is because of electromigration. Horizontal axis is current density. So you see, as current density increases, the ion velocity goes up. But there is a current density where it intersects the zero axis, below which there is no ion migration. So that's what we want to determine. In other words, under what conditions of current density and joint thickness will we have manageable or low electromigration. So as I mentioned, we want to take advantage of back stress. This phenomenon was discovered by Elon Black And this is a potential way of reducing the rate of electromigration in solder joints. I mentioned stress. There's also chemical gradient because bismuth is being pushed to one direction, so its concentration is increasing. So there is a chemical gradient, and that may also cause pushback. So there are two mechanisms that can cause this pushback. So either way, there is potential to reduce electromigration when we have low solder joint height by taking care of the mechanical and the chemical backstress. So just to give an idea of some scientific experimental work we have done recently on tin bismuth. So this is a simple but a very novel test we came up with. And in this, so in the middle picture, so this is the IPC test coupon we use for surface insulation resistance. And we are using this now to study electromigration. So what we did was we formed solder bridges between the copper lines. So if you look at the picture on the left top, so the red are copper lines, you have the top view, and we formed a solder bridge between the copper lines. And the very top we have the cross section. So you can see the copper lines and the solder in between. So now we can pass current through the solder and look for electromigration. And the picture on the bottom right is a scanning electron micrograph, which shows that bismuth moved up because of electron flow, and there's a crack in the joint. The picture in the middle bottom, this is what's called dot mapping. So it shows concentration of bismuth on the top and bismuth tin below that. So essentially the bismuth is segregated. Now, one issue with studying electromigration is to know the temperature of the solder joint. That's important. And we have a good technique of measuring the temperature of the solder joint very accurately. And at the bottom left, I'm just giving an example of Joule heating above the ambient versus current density. So you can see it's a very well-behaved plot. If you, as you increase current density, the Joule heating goes up. And the picture on the top right is a summary of the data we collected. But I'll show that on the next page. So here's the summary of the data. So on the vertical axis is the rate of change of electrical resistance versus inverse temperature. So you can see this is a very well-behaved data. And you can see that at 1.2 kiloamp, the resistance change is low, and at these higher current densities is the resistance change is higher. So, but these are just simple exploratory experiments we have conducted, but the actual testing will be done on LGA hardware that Rio is going to describe. So Rio, all yours, please.
Okay, thank you very much, PJ. I'm Rio Espandiar here, co-chair of the project, and I'm going to talk about project objectives and cover most of the how many phases there are and what's involved in them. This slide gives you the project objectives. It's the electromigration, as PJ said, is known to occur in most solders. However, the extent of electromigration is dependent on the envelope formed by the solder joint height, or also called solder joint thickness, the temperature of the ambient in which the solder joint is, and the current density flowing through the joint, as well as the surface finishes of the terminations like on the PCB land or the component termination, and the solder which the solder joint is formed with. So the objective of this project is to define this envelope for the solder being evaluated, which in our case is the low temperature tin bismuth solder. This information that we get from the phase one will define the conditions under which an electronic product will be expected to operate reliably over its lifetime. The project is divided into 3 phases. The phase one will establish an appropriate test vehicle to study electromigration. Since the solder joint height is a key variable, achieving the various selected solder joint thickness, heights or thicknesses will require some process development, and this is included in phase one. As PJ described, there is a back stress effect during electromigration. This back stress appears to diminish the stress within the solder joint, the electromigration within the solder joint. This phase will therefore investigate the role of the stress, back stress in reducing electromigration as a function of current density, temperature, and joint thickness. This will be done both with and without the nickel diffusion barrier at the solder joint to termination land interfaces. This being done with the use of iNEMI surface finish, which has nickel as a barrier, diffusion barrier. If the element that segregates due to electromigration is brittle, bismuth being one such element, then the solder joint reliability of the will be the solder joint that is subjected to electromigration will be impacted by the amount of segregation happening. This effect will be studied in phase two. Other variables that we keep constant in phase one will also be varied in experiments in phase two. Such variables are the land surface finish can be expanded over and above our copper OSP and iNEMI that we use in phase one. The land or pad design, whether it's solder mass design or otherwise, and metallurgical composition of the solder, which in our case is going to be the pure vanilla tin bismuth eutectic solder with nothing added. Once the empirical reliability data is collected from this earlier phase, then phase 3 of the project will entail development of an electromigration model, and with it the validation of various use conditions prevalent in the computer industry. Electromigration in solder bumps can be modeled with a finite element tool called COMSOL, C-O-M-S-O-L. The migration of vacancies themselves can be modeled by solving a transport equation which includes flux contributions due to vacancy gradients, electric field gradient, hydrostatic stress gradient, and a temperature gradient. In a broader scope, this COMSOL tool provides the ability of generating time to failure, TTF, prediction for different sizes of solder bumps in a range of current densities and temperatures. Next slide. So the phase one, what will the phase one consist of? This includes the design of the test vehicle for the study. It also includes the experimental plan, which would review and select and reviewing and selecting the critical variables which are part of this experimental plan. The test vehicles, once designed, will be assembled through the SMT process and electromigration experiments subsequently conducted. After the experiments are completed, the results will be analyzed and the impact of each variable will be understood. Failure analysis of pre and post electromigrated joints will be conducted by collecting solder microstructural images and documenting key data in those images, such as grain size, grain orientation, IMC characteristics, and even presence of voids, as PJ showed in his first couple of slides. The scope, the resources, tasks, and schedules for these two phases, phase 2 and 3, will be drafted after phase 1 is completed and a report is published. Phase 2 and phase 3 contents are still open. Next slide. This slide defines what the project covers and what it does not cover. Solder pastes in the thin bismuth system will be used to form solder joints for electromigration evaluation. We're going to use solder paste with no clean flux in them. So surface finishes looked at will be copper OSP and electroless nickel immersion gold, also known as iNEMI, as I said before. The eutectic composition of the solder in the thin bismuth will be evaluated. Of eutectic thin bismuth solders, such as having less than 57% bismuth, or ternary alloys such as tin bismuth silver, or even alloys with dopant additions to improve their properties, will not be evaluated in this phase 1. Solders joints akin to bottom termination components such as QFNs will be studied. These joints are in the 50 to 150 micro thickness range, which is much less than that for BGA solder joints, and apparently are more at risk for electromigration than the BGA joints. In other solder joints, such as chip components or leaded components, such as QFPs, SOICs, they will not be evaluated. Microstructural characteristics of the solder joint, again, pre and post electromigration, will be studied. This will also include the interfacial regions of the solder joint with the packages and board lands, where intermetallic compounds are usually formed. And these compounds have been known to impact the quality and reliability of the SMT joints. But the bulk solder joint characteristic will not be evaluated. Next slide. This slide shows the diagrams of solder joint stack up that will be evaluated for electromigration. The 3 different heights, as I mentioned before, height is big factor here, and you can see the 3 different heights, the bottom one being short, the center medium, and the top one tall. And then the surface finishes as identified by the brown one is the copper OSP, and the gold, yellow gold color is the iNEMI. So these 3 different combinations of these 2 surface finishes are possible depending on direction of current flow through the joints. And these 3 combinations are also showed here. In one case, for instance, the current will flow from the OSP land through the joint to the iNEMI land, and then the other one, it will be from the iNEMI land down to the OSP land. So the current direction which will determine how the bismuth in the tin bismuth moves will be different for the 2 joints shown here. Next slide. This is the DOE, the design of experiment tables and the various elements and their various variables and their levels. So it's a 3x3 DOE. The 3 variables are solder joint height, current density, and ambient temperature of experiment. These variables have been chosen after looking at the design of the test vehicle, as well as how long it would take for some electromigration effect to occur. The current density of 0.52 kiloamps, 0.5 kiloamps per centimeter, 2 and 5, and temperature 60, 80, and 100. The solder joint height will be varied by varying the amount of solder paste printed on the land before SMT reflow, and that solder paste will be varied by changing the stencil aperture. The table is shown there. Since it's a 3x3 design, it's 27 legs. We also added the SAC legs, but SAC for comparison. But because the SAC solder has a much slower electromigration than LTS, only the legs with the 100 degrees C temperature have been added. And below you can see the number of package cards and daughter cards that are required for this test. And I will go into what is a daughter card and package card and motherboard shortly. Next one. So this is the test vehicle cross section. On the left here, the top first green bar, and underneath it is what we call the package substrate. And that is attached to the daughter card. The two joints that will be studied for electromigration are A and B. The section below those two are what the design is for a 4-point test for measuring the current with applying voltage, and that was designed by PJ. And you will have the daughter card will have each daughter card will have two test solder joints, and it will have a card edge connector. Now that card edge connector will be inserted in a connector that is on the motherboard, that is shown on the right. And so you have 5 connectors on that motherboard, and you can insert up to 30 there daughter cards, and then use that to measure the electromigration once you put it in the oven at specific temperatures. And you can also vary the amount of current going through some of these so that the current density can be varied. Next slide.
Did I skip one?
I think, yes, this is one. Yes, so this is the preliminary schedule in the form of a Gantt chart for phase 1. This timeline, the extreme left column is starts from the project sign up when all the participating members are confirmed. And the estimated duration is just an estimate right now is 12 to 18 months. Once we start doing the experiment and we find out how long it takes for the electromigration to occur, that can be narrowed down once the time to finish is done. It can be narrowed down. And so we can probably adjust the schedule after that. Next slide. This one here shows the participation and the resource requirement as well as risks. We have a team that has been meeting weekly for the past 2 or 3 months to lay the foundation of the electromigration project, this LLTS electromigration project, and draft its statement of work, which I think has been shared. The participants in this team include engineers from IBM, Calci, Dell, Heraeus, HP, Indium, Intel, McDermott Alpha, Leuven Superior, Nokia, and Purdue University and Shinko. So it's a wide gamut of folks in the industry. Resource requirements have been identified. These requirements are listed on the table here below. They cover 5 different segments of the project work. Materials, test vehicles, test vehicle assembly, electromigration test, failure analysis. Potential contributors for some of these segments have been identified from the team that has met before, but the final commitments will be secured after the project is initiated. Some things that may require to be bought, I'm not sure yet, but those will be component substrates, daughter cards, motherboards, and the connectors that are put in on the motherboard. These may need to be purchased, but the project team set a limit of $1,000 for each participating company if there is such cost involved. And I think I am done with my section. Haley, I think you are starting the next one.
Thank you, Rio. So I will explain how to participate in the project. So as mentioned, we will have a sign-up due date by the end of this month. iNEMI membership is required. So we have a project web page set up. There is a link. You can download the project statement of work and also the project statement agreement that need to be signed. So those 2 documents are available on the website. So for the members, if you decide to join, you can just sign the project statement and send back to me. A soft copy is fine. Then we have iNEMI VP of Technical and Project Operations, Grace O'Malley. She will sign and approve the participation. Okay. So as mentioned, to join the iNEMI membership, please contact me. Let me briefly share the project statement, just to give you some idea what you will need to be done to fill the form. Okay, I hope you can see this document. So this is project statement for this project. So for company who decide to join, you need to fill this, and you put your company name here. And basically, this document is to agree with the iNEMI project management rules and the policy, and agree with the plan, the project statement of work. Okay, so if you have any background technology that will be disclosed in conjunction with this project, then you should choose DAS and also send a separate declare document. So to clarify what's the technology you will disclose and what's the status, if it's a pattern or whatever. Okay, if there is not, you just choose does not. Okay. So the next several items here is really describing the contribution to the project, including the participating in the project meetings, probably need extra hours to accomplish the tasks, and then about the the material or the process or any tasks need to be accomplished to contribute to that. But certainly this is depend on what resource you can offer or what capability you have. So you can fill in the, we have a table similar as what PJ and Real showed in the presentation about a resource list. Just to indicate where you may be involved and support. So we put a very small budget there, $1,000 as a maximum exposure per company. This won't happen before this expense really occur. This is just to make sure that if we really need to purchase any test board or component, because as Real introduced the test resource and assembly, we already identified the resource. Okay. So then if it's we call it affiliated organization as an iNEMI member. For example, the university institutes or some industry associations, they are waived for the project expense if it happens. Okay. Then we also accept material donations from non-members. For example, if some company, they are willing to contribute to the PCB, right, or the components. We are willing to accept that and include any materials. But they will only, because they are not a formal project participating member, they will access only the data relevant to their contribution. Okay. Then the following is just to describe to the project will adhere to the IP policy and the data management rules. Basically, the project is owned by the project team members. So the team members will decide what information will be shared within iNEMI membership or with the public. Okay. So we have some other rules about the data management and publish the results. You can go through that when you download this project statement. Okay, here is the table I mentioned to input if you have any contribution you foresee that you are willing to share or contribute. Okay. So including materials, test vehicle, field analysis, capability, or any other that you see there could be a need. Okay. So for the sign up page, we require one form need to be signed per company. So if you have multiple people in your company plans to join the project, you can just have one representative to sign this document and let me know who are the people will be included in the project distribution. Okay. The management signature will be required as well, just to make sure that the participation and the contributions are agreed and supported by the management. Then after you finish that, just send the document to me. In Grace O'Malley, she will do the acceptance approval. That he will send back to you the finished document. That's the loop of this sign up. Okay. For the signature, it's acceptable to have digital signatures, right? To make it easier. I think that's all I want to explain. I think now let's open up for the question and answers. Okay. I saw a question earlier about the recording sharing. It will be shared together with the presentation by early next week. Are there any questions? If you have, you can unmute yourself to speak out. You
Rio,
also can.
I have a question.
Go ahead.
Hello, can you hear me?
Yes, can hear you.
Yeah. Rio, what is the meaning of why we do the EBSD analysis of the solders? Any idea?
Yes, the reason is that sometimes the grain orientation may affect how much of the bismuth is moving and going to one side of the joint. I think PJ, do you want to add something else on that to shed more light?
Right. The reason is tin, diffusion in tin is very anisotropic. The diffusion in the C direction is very different than in the A and the B direction. So it's good to know the grain orientation in a solder joint.
Yeah, in the past, some literatures have stated that that may play a part in how much why you see some difference in the solder joint. But this being tin bismuth solder, it's not as it's a little bit different than doing the same with SAC solder joints. So just keep that in mind, Murli.
Yeah, thanks, Rio, and thanks, PJ.
So there's a very good paper by Tom Wasik on this project, on this idea.
Yeah, is it on tin bismuth or SAC?
I think, okay, I forget. I think it's SAC, but I'm not sure.
Yes. So that's a little different than tin bismuth may not have the same grain orientation, various grains or sizes as our LTS does.
Sure.
Yeah, thanks for the info.
Mm-hmm. Yeah, Haley, I would just like to add for everybody on the webinar that if you can look at the SOW and if you have comments, please write it up and send it back to Haley. I know a couple of people did that when we were in the US webinar yesterday.
Okay. So question from Jeffrey. He asked if the project will use SAC as a control. I don't think it's a control, but it's will be included as a comparison. Rel, you want to comment?
Yes, I think to do apples to apples comparison, you have to run all 27 legs on the SAC as you do in the LTS. But the problem is that if you go to lower temperatures, lower current densities, the LTS may take months to fail. Correct, PJ? That's what people are saying. So we don't want to drag the project on for that. We know that SAC does not have electromigration issue. This has been used since early 2000s in the industry, and there haven't been any electromigration issues at least highlighted. So we know that is why we just wanted to compare the 100 degrees C high current density values for with what we get for tin bismuth. That was some other questions that were all were being asked in our team meetings. How does this compare to SAG? How, that's something we don't know yet until we do apples to apples comparison. That's I hope I've answered that question here. If there are any other alloys people want to look at, that can be thought about in phase 2. But phase 1 will stick to the tin bismuth and partial DOE of the SAG.
Okay. Any other questions from audience? Oh, so yeah, we have someone ask where is the share screen. I don't think we are sharing. Do you have any particular question regarding the presentation? So any other questions to the project? Okay, if not, I think we will close today's webinar. I would like to thank you all for attending. I look forward to work with you on this topic. If you have any questions you think of later, you can contact me as well. Okay, I would thank Real, PJ, and Hammond to lead this project. Okay, look forward to work with you guys. Thank you.
Thank you.
Have a nice day. Take care.
Bye.
Thank you. Bye-bye.
Bye.